right, so we did the spontaneous or voltaic spontaneity. The whole purpose of that form was, and that lecture was to help you tie in the concepts of what voltage really means, and it means there's a pathway. So I'm not going to give away all the answers. Some people are still working through this form, but I do want to review it a little bit. Once the forms are definitely done, and I've been opening the forms up a little longer because some people don't know where they are or whatever. Okay, trying to get over maybe, I don't know. Like I didn't know there was another page. Yeah, there's a whole other web page or whatever. So people haven't been through my craziness before, all right? Or I guess if I write too much stuff, you don't read any of it, okay? Any case, let's go through this. We talk about solution now. We should have that down. That means we're talking about ions that have been pulled apart from a crystal. Why? Weak Coulombic attractions. And we should be able to identify that now. Okay, and obviously we put aqueous. That's a Kardashian wedding because, well, party people, okay? That really means you have what? Na plus and chloride ions who've been separated by the water's attractions. They're free. That's the whole point, all right? And so as we go on, we have these drawings. And these represent the famous boyfriend, famous girlfriend stuff that I talked about. Hey, these guys were hand in hand. A positive attracts a negative. Silver nitrate is a salt. It has a crystalline structure just like this. It's a one-to-one crystal. That's why there's one silver ion to one of these, the grouping of atoms that have a charge collectively. We'll study them in more detail. But the reason they've been pulled apart from the crystal is the positive part of water, okay, which, by the way, is the hydrogen. And there's a pair of electrons that exist between them. But they're not being shared equally. Those pair of electrons have been pulled into the oxygen. So that means that this area right here is more dense with electrons, and that's the negative end. This hydrogen end is positive because electrons have been pulled away. Bottom line, these positives attract this negative. And if all these waters are surrounding this ion, they can't feel the attraction to the other. That's how dissolving works. But it only works if the attraction of these ions coulombically are weak enough so that water can can compete for those charges. If this was a -2 and a +2, game over, water's not strong enough to pull it apart. That was the point I was trying to make. And notice the orientation. It's important you get this. The positive part of water is going to surround the negative ion. The negative part of the polar water surrounds the positive. Okay? Just like I said last night, all the guys surrounding the famous girl and all the gals surrounding the famous boy, and that's kind of the famous boyfriend analogy. Okay, what I'm giving you here, okay, is part of what you're going to see in your Regents Chemistry folder. Regents Chemistry reference tables. Your reference tables have something I'm going to give you. I'm going to give you, for any test or quiz we sit down and do in class, I'm going to give you the full complement of Regents and AP Chem reference tables. I don't believe in memorizing. So these are solubility guidelines. What does solubility mean? How well will the ions in this crystal be pulled away from water? It comes down to how strong these guys are attracted to each other coulombically. For reasons we explained, Coulomb's law persists. So when I say soluble, is the water able to surround these and pull them away from that animation I showed you? Okay? There are so many things in chemistry a lot of teachers make their students memorize. I hate memorization because there's no meaning in it. But people will make you, people will force, okay, I'm not going to continue. Can I X out of that? You're going to make me do it? They didn't I don't want to get out of this. It's forcing me to continue. Oh, just continue on. Okay, thank you. A little brain hemorrhage there for a second. Okay, now, so this is part of the solubility rules. But I'm going to put up all the solubility rules. And the teachers will make their students memorize these. Obviously, if you have a reference table, you don't have to. Now, this is a condensed version. There's more. But there's a general rule, okay? And it's so gosh darn simple, okay? And it's logical. I want you to understand. So I'm showing you ions. And what they're saying in this reference table, which, by the way, you'll have. You don't have to memorize them. But I want you to understand, okay? What do we have here? If I'm soluble, that means that these ions in a salt break apart and become free. Well, look at these. Why are these always soluble? +1, +1. Group 1, all their +1. Their charges are small. Hey, this is -1, -1, -1, -1, -1. These aren't positive, but they're small negatives. Coulomb's law is what? The force of attraction is the size of the positive, the size of the negative, over the distance squared. If these charges are low, the force between the ions is low, and they can be what? Pulled apart and dissolved, making aqueous Kardashian wedding. Okay? Oh, what about the ones that are insoluble? That means that water can't get in here and pull these apart because the attractive forces between the ions are too great. Well, look at the size of the charges here. These guys are tremendously benign. You say, oh, there's a -1 there. There are some small exceptions. Like this is a -2. There's an exception. We're going to learn about those exceptions. But most of these you can eyeball, right? Okay, and you can see by the size of the charge, okay, and you can predict their solubility. Because when the charges are high, the force is high and water can't compete, okay? Now the question is, okay, what if you put a big with a small? Big charge with a small charge, and that's where I was after today, okay? I was after last night a little bit. So this is this question right here, okay? How do I look at this? Now, by the way, I see why there could be some problems. Now, we know that sodium right here is +1 and -1. Small charges, well, guess what? It will dissolve. They will be free because they'll separate from the crystal. And of course, we call that a solution. We call it soluble, okay? Now, what about magnesium chloride? Mr. Grotsky, I don't know what the charge is. Well, group 1 are always +1. Group 2 are +2. Why? These guys lose 1 to be stable. These guys over here lose 2. Or you can go to your Regents chemistry table and it tells you what charge like to become. Bottom line here is +2. Chloride likes to gain 1. Chlorines like to gain 1, so they're -1. So I've got a +2, pretty high charge, but now it's cooked up with something that's -1. What do I do there? Because now you're giving me both. I want you to think with me for a second. Okay? If I'm +2, let me do it this way on the board. Okay? So let's do +2 right here. This whole thing is +2. In a small area, I've got +2. I would call it a high charge density. It's a lot of charge in a small area. You with me? Now, when it hooks up with something that's -1, they tend to be bigger. You're stretching that -1 over a big area. That is a low charge density. So when these guys come together, right, this guy only feels what? A small percentage of the -1. Therefore, it's going to be a weak attractive force. Look at the rules, party people. If I'm -2, -2, -3, those are high charges, right? I'm insoluble. But there are exceptions. What are the exceptions? When you're hooked up with someone that's +1. Hooked up with someone that's, okay, group 1. What's group 1? +1. Look at your exceptions. Okay, so it kind of makes sense. All right? And the famous one is, look at nitrates. Nitrates are -1. But think with me for charge density. How many atoms here? There's 4 atoms in the cluster, and spread out is a -1. Low charge density. So even if you have something that's +2 or +3, when it hooks up with a nitrate, it's always soluble. Nitrates are always soluble. Okay, which means you have the famous boyfriend, they break apart. It's important you understand that as we're going to apply it to the Daniel cell today. Okay, so moving on. Moving on. Okay, I want to move all the way down to this right here. And I want to do this experiment. I talked about it last night, but I want to do this. This is showing what over time? That the concentrations of the NO2 and N2O4 become constant. What does that represent when the concentrations remain constant in the reaction? It rhymes with equilibrium, exactly. Equilibrium. Okay? What's equilibrium? Equilibrium in when there's no noticeable change because the forward reaction rate equals the reverse. Hey, bottled water, greatest example. Right now I can look at that line and mark it, and I can wait till the cows come home, but that line won't change. Now I don't have any cows, it's gonna be a long time, but the point is, and I know that I'm moving it, that line of water is not gonna change. Why? Because as fast as it's evaporating in this closed system, some of it's what? condensing. It has reached equilibrium. If I take the top off, rate of evaporation will be faster than condensation, and it's going to go down. But if it stays constant, you've got equilibrium. Equilibrium is boring. It looks like nothing is going on. It's even worse. Equilibrium means there's no actual preferred direction. Stay with me for a second. If I start with 100% NO and 0% N2O4, let me write the reaction for you. Let's get this off the board. I'm trying to use every piece of equipment today in this lecture. Okay, just kidding. Get this off the board here. Let's write the reaction. And I'll leave that for those that have OCD. I'm helping you. Okay, now, I'm going to take 100% NO2. And it's going to become N2O4. It's kind of a lie because you actually need two of them, right? Two nitrogens. So two of these come together. And we call this a dimer. Two of these come together and stick together and become one particle. But as fast as they do what? When they reach equilibrium? Make this decomposes. And that's where you get a constant level. So this has reached equilibrium. How do I know? I have some. Okay? I had some ice in there too, but it's not going to work so well. So here is an example of an ampoule. This is a glass tube that has a brown gas in it. It's not a brown glass tube, it's a clear glass tube. Because in here I have both gases. Let me explain. Okay? Here is the brown gas. This gas is colorless. How do you know I have reached equilibrium? How do you know I've reached equilibrium? Is the color getting darker? Or is it getting lighter? Or is it staying the same?
There's no change.
There's no visible change. Now, in truth, there are NO2s becoming N2O4, but that's happening as fast as the reverse. There's no preferred direction, so therefore there's no net change. That is a death of a chemical reaction. Chemical reactions or processes move when there is a preferred direction. If this was a voltage in a battery, what would the battery be? 0 volts. Right, there's no work being done, no energy given off, no preferred direction. That's called equilibrium, is the death of a cell. Cells die. Cells, reactions have to go forward. Use the glucose to get the energy. Okay? That's important. All right? Now, but wait a minute. It wasn't in equilibrium, was it, when it started? When it started, I had 100% NO2. Remember that U diagram? Hope you guys liked it. Okay, because here it comes again. This is 100%, I'll change colors to make it pretty. Okay, this is 100% reactants. We'll say NO2. This is 100% N2O4 products. What's that mean? This is where? Equilibrium, death. No overall process. Now, things in nature always move toward equilibrium because at equilibrium there is 0 free energy left. Free energy is the energy to do work. If a reaction is going one way, it has the energy to create, it's producing free energy. Batteries go one way until they die. We can use the energy. Once the battery reaches equilibrium, there's 0 volts. There's no energy to use. So things in nature always work toward equilibrium. So party people, if I start with 100% NO2, look how far away I am from 0. It's going to work spontaneously downward. And the best way to think about it is the arrow. Look, if I'm in this position here, look at the size of my arrow to get to this position. That's showing me a huge direction. But wait a minute. As the reaction proceeds, don't I start building up some N2O4? So as the reaction proceeds, I'm no longer at 100%. I might now be 90% NO2 and 10% N2O4. And now I'm where? That makes sense? The percentage of my reactants going down and the amount of N2O4 is going up. I'm getting closer. Where's my arrow now? Is it as big? As it keeps going forward, what's happening to the size of my arrow? Right. And the size of the arrow is the direction, is the spontaneity. When I get to this position, no more arrow. There's no preferred direction. There's no change, as you see. So that's important, okay, to understand that we are shifting to the right here, okay? Now, some other things here, all right? If it's at equilibrium, we can play God a little bit, okay? And this is important, because what we're going to do in the Daniel cell, we're going to play God, or we play nothing if you're atheist, okay? Or play Buddha, or Confucianism. No, that's not a religion, but you can't play that. But in any case, let's pretend we're at, let's not pretend, let's put it right here. Let's start at equilibrium. Because guess what? That's where I am. Okay? Now, stay with me for a second. What if I was to increase the amount of NO2? I was at equilibrium, and now I'm going to increase NO2. Wouldn't I be now here? Where would the reaction shift to? When I say shift, I mean now be more spontaneous in what direction? Wouldn't it go this way? At equilibrium, it wants a certain amount of both. I'm adding more than the universe is allowing. So the reaction is going to move in the direction of equilibrium, and to do that, it's going to move to lower the NO2. Now, there's a way to think about this. It's called the Chatliers Principle. I'm going to show you an easy way to think about this. The Chatliers Principle states, if a process is reversible, many batteries are. The real reversible batteries are the ones that are rechargeable. But anything that's slightly spontaneous or reversible deals with the Chatliers Principle. And the Chatliers Principle states, if a reaction can or has some reversibility, if you apply a stress to it, it's going to always undo that stress and work in the opposite way. Let me explain what that means. So here's the stress. This is what humans do. This is what chemists do to make reactions more spontaneous. This is what the reaction does. We'll do this in different color to keep it kind of cool, okay? This is called a response. You know what this response is? The reaction just working toward equilibrium, going from high free energy to low. So the stress is, I was at equilibrium. What if I was to add more NO2 in there? Watch what happens. So here's the stress. I'm going to increase NO2. The Chatliers Principle states it's going to do the opposite to regain its balance. So if I push on Emma, she's going to fall over unless she does what? Pushes back opposite. So here's what I just did. We're here, right? I added more NO2 than I'm supposed to have at equilibrium. Isn't the reaction to work toward equilibrium again? Aren't I going to shift to the right? If I have more NO2 than I'm supposed to have, isn't the response, new color, isn't the response, the reaction to become more spontaneous this way? That's what it means. Now, if you're more spontaneous that way, aren't you going to use up the NO2 as you move toward equilibrium and make more N2O4? Yes. So one of the way chemists keep making a reaction that may not be very spontaneous, we keep adding more reactants into the what? Into the reaction chamber to keep it going forward. By adding more reactants, we move this up. We increase the NO2. What's the response? Lower NO2. What's another way a chemist can play God? Okay? So let's say I'm right here again, equilibrium. What if the stress is I lower N2O4? Now by lowering N2O4, don't I go this way? Right, this is 50% N2O4, 50% NO2. if I lower the N2O4, I'm now where? Where's the reaction going to move towards? And the shift is going to be where? To the right again. Now why does that work? You decrease N2O4, check it out. The response is going to want to do what? Increase N2O4. And if I shift to the right, which is the same shift, aren't I going to make more N2O4 and use up these guys? So how does the chemist make the forward reaction even more spontaneous? We pump it up with more reactants. We take away the products as it's being made. You ever see those very famous chemical experiments where tubes are connected and the chemist is talking or something and they have like dry ice with like fog in the background just to make it look cool? Those setups are normally used to take away the products. The cell works that way. We got to keep reactions going forward in a cell. We don't want equilibrium in a human cell. They die. So what do? We take the ATP and use it. If we're making ATP in cell respiration, it builds up, it's going to stop the process. We dead. So we pull the ATP away. What do? We lower the product. The reaction what? Shifts to make more. Now, how about things that are bad? Check this out. How can I really kill this process? Start here again. Sorry. Just flipped out there. Okay. Put my cap back. Got nervous. Okay, so now I'm down here. What if I do some bad stuff? What if I take away a product, a reactant? If I lower NO2, what's the response going to be? Forget about the U2 diagram. I lower something, what's the response by the reaction going to be?
It's going to go up.
Yes, to regain its balance. Now that's oversimplified, but you can use that even on the AP. Oh, NO2, sorry. And how would it do that? How could it increase NO2? How could it do that? How does it respond to increase NO2? The only way to increase NO2 is to shift where? To the left. We call that a Beyonce shift in chemistry. Very famous chemist, John Beyonce. It just so happens that Beyonce was a student of chemistry and she wrote a song to the left. Okay, don't please me. That's fine. Now, it's going to shift to the left because you're going to make more of this, right? And use up. Whoa! That makes the reverse more spontaneous. What just happened here? I lowered NO2. Uh-oh. By lowering NO2, isn't there going to be a higher percentage N2O4? How's this reaction work now? It's going to be more spontaneous in reverse. That is that. This is Le Chateliers' principle. What do you think this would do to the battery? If I had a battery and I was to decrease one of the products, I'm sorry, if I was to decrease the reactant, what's that going to do to my voltage if I'm making the reverse happen? What's it going to do to my voltage in my battery? If I make the reverse pathway,
would it be negative?
It would eventually go negative, correct. Or you could say that the volts would drop. Now, generally speaking, we don't start here in a battery. Batteries start, they're spontaneous, they're working. What happens over time to the voltage?
It goes down.
Goes to zero. Why? Why does a battery go zero? Batteries are going in one direction. Not like the band, though, because I'm not really into them, but this goes in one direction. That means what? I'm using up NO2, correct? If I'm using up NO2, all right, that means that this is building up. Okay, well, if I'm building up NO2, it's moving downward. Or think of it logically. If I've got less reactants, there's less of them that can react, correct? It makes sense, yes? All right, so that's Le Chateliers' principle. Okay, now there's one other thing with Le Chateliers' principle. There's heat and pressure. So let me go over that, and I'm going to apply this beautifully, hopefully, in front of you with the Danielle cell. So let's do this. Okay, let's do a demonstration. So now we have, okay, heat. We did increasing and decreasing. Now, we're going to learn in thermodynamics, the forward reaction or the reverse is either endothermic or exothermic. I don't care if you don't know this yet, but, all right, I'm going to put it in here. Let's pretend that the heat in the reaction is right here. This would be an endothermic reaction. That means that these two chemicals need heat to go this way. Or the reverse is exothermic. When this goes this way, it releases heat. But heat's going to be one way or the other. In a physical process or a chemical process. If you don't know that, or that doesn't sound familiar to you, hey, think about ice. H2O solid becomes H2O liquid. Don't you need heat to melt solid ice? You need this and heat, so that's why melting ice is endothermic. And again, we will get into those things later, but the heat belongs somewhere. Okay, so when I write the heat in, I'm pretending the heat is here. So now instead of stressing in terms of how much stuff we have, I'm gonna change the temperature. What if I increase the temperature? What do you think the response is gonna be to regain its balance? Decrease temperature. Now how can I decrease the temperature? Treat temperature like a reactant. How can I decrease the temperature? Well, I either go this way, Beyonce Shift, and make more of it, or I go this way and use it up. Which way would it shift to effectively lower the temperature? It'd have to shift this way so that you use up these guys, including the heat, to regain your balance. That make sense? Okay. Now, in truth, heat isn't a reactant. It actually changes the equilibrium constant, but I still wanted to present that to you today. Okay? And let's talk about that. We don't know where the heat is. Check it out. Let's use the Chatliers Principle. Let's do this. So right now, there's no change, correct? Okay. So I've got these two tubes. Same color, right? Right? Put them right next to each other. I think one is, they're about the same color, right? I'm colorblind, so it's hard to tell.
They're good.
Are they, okay, they're the same. Okay, so I'm going to take this one, doesn't matter. I'm going to put it in some hot water. I'm going to heat it. So I'm going to increase the temperature. The reaction is going to shift to lower the temperature. Now, in this kind of backwards way, we're going to figure out where the heat goes by the color change. The color change is going to happen. I know what the color change is supposed to be. Here it is. That's room temperature. Okay? Okay? And I don't know if you can see it, but I'm heating it. Did you guys notice if it did anything? It's not like it's not going to go colorless on you, or completely black. But okay, so now it's warmer. I don't know if you can see it. This is the one I just put. Can you see any difference there? It's darker. The one that I put in the heat is darker. This is the one right to the right that I'm moving. Okay? I don't know if you can see that better this way or not, but that's going to be darker. Okay? And we'll see that as it heats more. Why did that work? It got darker. Which one has color?
NO2.
Right, so by heating it, where did it shift? If it got darker, I moved it out of equilibrium, and I'm producing more of the brown. Where's the shift?
Left.
To the left, a Beyonce shift. And therefore, it shifted to the left when I increased the temperature. It shifted to the left to do what? Decrease. Where does the heat have to be so that a shift to the left causes a decrease in temperature? Where must the heat be, right or left side? We heated it. It definitely went left to make more dark, more brown. And that was needed to lower the temperature. Where's the heat? Well, let's think about it. If the heat is over here, wouldn't I be making more heat by shifting to the left? I'm trying to lower the heat by my shift. So where is the heat located in this reaction?
The right.
To the right. By it shifting to the left, I'm using this up, using that up, and I'm getting the balance back. Okay, now it's going to be warmer. Now it's getting real dark now, right? Darker. I know it's not sexy, but you definitely can see it's dark. Okay? Well, let it sit there. All right? Now, what if I throw in an ice bath? It still, yeah, it should, definitely, you got it. Now, except my ice has, of course, melted. So liquid nitrogen, this would go pure clear. Pure clear? That's kind of weird. But it should get lighter. So in a cold temperature, it's lighter. In a warm temperature, it's darker. Why is it going lighter? What's the stress here? The stress is I decrease in the temperature. The reaction wants to do what? Increase the temperature. So where does it shift to?
The right?
Yeah. And it supports where the heat is. You're not going to flip the heat. The heat's either on one side or the other. So both of those tests support that. You with me? Cool beans are chilled. All right. And this is getting very dark now as it's getting heated. Okay. All right. Whatever. You don't believe me? It's good. Now, let's apply this to the Daniell cell. Oh, we have one more thing. Pressure. Okay? So we got heat changing concentrations, and now we have pressure. Okay? Okay, now, when you're dealing with pressure, pressure is due to gas molecules flying around at 100 miles an hour. What creates pressure is the collisions. So anytime you have a pressure type of stress, you have to count how many molecules of gas you have. Okay? So let's do a stress. I'm going to increase the pressure. What's the response going to be? Decrease the pressure. Now, let's count how many gases we have. Gas, gas, gas. How many particles of gas here? How many particles? Each one of these is a molecule, is a particle. Two. How many gases here? If I increase the pressure, where is it going to shift to make less gas? Who has less particles? It's going to shift to the right to lower the pressure because two particles become one, you have less collisions. Anytime you have a pressure stress, count how many gases. And if you increase the pressure, it's going to move to the side with less gases, less pressure. Now, what if there's no gases in the reaction? No effect. What if these are both two? No effect. Let's do the opposite. I decrease the pressure. Where's it going to shift? What's the response? I decrease the pressure as a chemist.
Increase.
It's going to increase the pressure. And now it's going to shift to make more gas. Okay? That's the Chatliers Principle. Don't forget, what is it really? Making the forward more spontaneous or the reverse on this U2. Everything works toward equilibrium, the death of a reaction. Okay, let's bring back our friend, the Daniell cell. And let's play God. Okay, or nothing. Cool beans. All right? I don't know how that worked. All right, I got 0 volts. Okay, so what do we got going on here real fast? Okay, if you remember, here is my zinc, right? Here is my copper. We can't see it so well, but hey, we can. All right, who's better at oxidizing, zinc or copper? Yeah, you better go to your net potential tables, which I tried to give you. Okay, and if I go there, here we go. Zinc or copper? Zinc oxidizes as positive 0.76. Copper does not like to oxidize. That's why we use copper pipes. It doesn't rust. Copper is what? Negative 0.34. So zinc is your anode. And what happens is zinc 0, solid metal. Every time a metal is 0, it's a solid except for mercury. Becomes zinc plus 2 and 2 electrons. That means a solid piece of zinc disappears as it dissolves, as it becomes an ion that's free. Now also, party people, in this solution, I have zinc nitrate. What is that? That means I already have some zinc plus 2 ions, and I have some nitrate ions that are free because it's soluble. You can see through it. You with me? Cool. Now, over here in this solution, I've got copper nitrate. What is that? Copper plus 2 is already in solution. That's the blue stuff. And I have nitrate ions. Now, this is my cathode because copper isn't as good at oxidizing. That does not mean that the cathode itself undergoes reduction. Red cap means reduction occurs at the cathode. Anox means that oxidation occurs at the anode. It just so happens in this system, the zinc metal is also reacting. Don't fall in love with always the anode is going to oxidize and the cathode doesn't. There's different systems. The electrodes are the place of redox. We're going to keep the redox separated from itself. Okay, now we're going to put this through a wire, connect it to a voltmeter. What's the cathode going to do? At the cathode, the copper plus 2 is going to gain 2 electrons. Where do those 2 electrons come from? Well, when the zinc oxidized, it's pushing 2 electrons from the anode to the what? To the cathode. The one who oxidizes pushes the electrons, and the one who reduces pulls. So the copper plus 2 is pulling to make what? Copper 0, another metal. This is plating. This is getting bigger. This one's getting smaller. Hey, can we measure the strength of what they're doing? Copper plus 2. Positive 3,4 in its ability to do that. It's positive. It's good at doing that. How about zinc oxidizing? Christmas. Zinc oxidizing, going in the reverse. It's positive 0.76. That's pretty darn good. I always reverse the one who oxidizes by convention. This is written by what? Reduction. I'm going to add them together. What do I get? Positive 1.1 volts I should get. Now, how come I got 0 volts? What am I missing? What am I missing?
This bridge is all.
Yep, I need to even these out because if I don't, I'll just get a fusion here. Okay, so let's connect this guy. Stay with me. I just have 2 more minutes. Okay, so the positive lead, like you're at what lab? Oh, Christmas. Goes to the cathode. Good enough. The negative lead, black lead, goes to your anode. Cool beans. And we got 0 volts. Why? What am I missing?
The salt.
Salt bridge. 0 volts. Oh, no salt bridge, 0. Salt bridge, you got volts. 0.74. I don't know if people can see that from home, but 0.74. Okay, now it's below that. Why? I'm running out of stuff. My battery's dying. Okay, now before we go, I'm going to play God a little bit. Okay? Moses. No. Watch. Why does this work? Well, this is made of sodium sulfate. Na2SO4. It's aqueous. It's a Kardashian wedding, so this is Na plus and SO4 minus. They're all over the place. -2. Now what's happening? When zinc becomes zinc plus 2, aren't I producing more zinc plus 2? This beaker's getting positive. How can electrons move away from positive? When this works, aren't I losing copper plus 2? I'm losing positives, correct? So this beaker's getting negative. Electrons will never travel to a negative. So to keep both of these electrically neutral, as zinc is produced, the negative ion balances that charge out to keep it electrically neutral. As copper plus 2 is lost, the Na plus comes down to replace the positive to keep it electrically neutral. Now, I want to increase the voltage. I want to do the Chatliers Principle. What's my overall reaction? Go fast. Zinc 0. Who's another reactant? Copper plus 2, you with me? Goes to zinc plus 2 and copper 0, right? This is my overall reaction. I want to make it shift to the what? Right more. Here's what I can do. What if here's my stress. What if I lower zinc plus 2? Won't the response increase zinc plus 2? Where's zinc plus 2? If I lower it, won't it shift? If I lower this initially, won't it shift to make more of it? And isn't this my shift? If I lower zinc, we increase zinc plus 2. How does this shift to increase zinc plus 2? It's got to go here. So I'm going to play God. I'm going to increase my voltage. You know what I'm going to do? I'm going to lower the concentration. I'm going to just pour water into this cell. I'm going to lower the available amount. Now, molarities are the ratio of the ions to the water. So let's just do this. Let's stir a little bit. Did it go up a little bit? Yeah, it's not sexy change, but it went up. Now it's 0.78.
9.
Oh! I added just water! Just water, and my battery's working better. Come on, that's cool. Why did it work? The Chatliers Principle. I made the forward reaction more spontaneous by understanding my shifts. I lowered zinc plus 2. Hey, what's that you do, Darbrand? I made the forward more spontaneous. Get out of here. Okay? I added water to my battery and it got better.